Hello there, welcome to StudySync. This is our first video in the series of algebra, and we are going to talk about introduction to number theorem. Okay. Now, when we talk about number theorem, we are basically going to discuss about some sets of numbers and look at some properties about them. And when we come to numbers, the largest possible set of numbers that we can think of is what we call complex numbers. Complex numbers encompasses every number we work with in mathematics. Now, let me try to represent this in a set. So this big set is what we call complex numbers. Now, complex numbers have what we call the real numbers. So we have real numbers and imaginary numbers. Now, a complex number is simply represented by, let's say, a plus bi, where this side represents the real component and this represents the imaginary. Now, in our study in algebra, we are going to focus on the real numbers. So the subset of complex numbers called the real numbers is where we are going to focus on. So when we talk about real numbers, they are the actual numbers in algebra that we can use for our mathematical calculations and everything. As the name implies, they are real. So fast forward, let's look at what real numbers entail. Now, real numbers also contain some subsets, and one of such, which is very common, is the set of integers. So when we take this to be real numbers, one subset is called the set of the set of integers. Now, integers, as we know, they are numbers that range from, they take positive and negative whole numbers. So when we talk about the positive and the negative whole numbers, including 0, then we form what we call integers. So on the number line, we can see from negative, let me say 3, negative 2, negative 1, then 0, including 0 itself, then 1, 2, going. So 0 inclusive. In fact, so it will be something like this. So this are the integers, including 0. Okay, in the real number set, one of the large sets that we can look at, or the two main sets that we can actually talk about, is the set of rational numbers and the set of irrational numbers. So they are complementary, so they are complements of each other. Whenever you make mention of the set of real numbers, then you are talking about what? Rational numbers plus irrational numbers. Now, rational number, as the name implies, it comes from the word ratio. So rational number is when you can have a number represented in the form a over b, where b is not equal to 0 and a and b are some integers. Then any number that can be in this form is called a rational number. That which cannot be represented in this form is simply an irrational number. So for an irrational number, the common examples like pi, you can't represent pi in the form a over b where b is not equal to 0. There is no way you can have pi represented in this form. An approximation to pi, which is, for example, 22 over 7, is an approximation. That's not the actual value of pi. So in this case, pi is also an irrational number. So now let's look at some of the properties of these sets of numbers. So let's take the first one, called natural numbers. Okay, so the first set of natural numbers, let's denote it by capital N. Okay, so the first set we are coming to talk about is the natural numbers, the set of natural numbers. So capital N. Now when we take natural numbers, so let's say for example, so it's an infinite set. So let's start. So it starts from 1. We also call this counting numbers. So counting starts from 1. So the set of natural numbers can be represented in this form: 1, 2, 3 to infinity. Now, one property we can talk about is the closure property. So of addition. Now if we talk about closure property, when we say a particular set is closed under a particular operation, it means when you take elements from that particular set and operate it with that particular operation. So some of the common operations we know are addition, subtraction, multiplication, and co. Now for addition, so for the operation addition, whenever you add any two natural numbers, you are definitely going to result into another natural number. So we say the set of natural numbers is closed under addition. So that's the first property. So closure property of the set of natural numbers. So the closure property of the set of natural numbers under addition. Okay, that's clear enough. Now the next one we can also talk about is commutative property. Now the commutative property of natural numbers in when you talk about addition, it means when you add any two natural numbers, so let's take a and b being some natural numbers. When you add the two of them, so a plus b is the same as b plus a, and that's what commutativity talks about. It means if we reverse the position of the operands and however you are doing it in the operation, you are still going to get the same result. So a plus b is the same as b plus a. Okay, now the next property still under addition for the set of natural numbers is the associative property. Now associative property, we are going to take three of such operands. So let's say a, b, and c. So let's say a, b, and c are some natural numbers, and we want to add them, a plus b. So we take two at a time. So addition, in the basic form, we can only add two things at a time. Then maybe what you get from there, you add it to the next. So that's basically addition. Now a plus b is the same. Then adding it to c gives you a result. It's the same thing you get when you add a to the result of the addition of b and c. So a plus b then plus c is the same as a adding to the result of b plus c. The next property we are going to look at is the associative property of multiplication. So as we saw previously, where we did the addition of three natural numbers, yet to the same thing we are going to do with three natural numbers where we are coming to multiply them. So at a time, let's say we multiply a and b, then the result we get, we multiply by c. It's the same thing as when we do a, then we multiply by the result we get from multiplying b and c. So this is the associative property for multiplication. Now let's look at the multiplicative identity property for natural numbers. Now identity means identity means that we are operating a natural number a by a particular number which we will be calling the identity element, and now we should result into what this identity we are talking about in multiplication. And in multiplication, when you do such, you should get 1. So let's say a multiplying, so multiplication, a multiplying b should give us, let's say, 1. Then b should be our multiplicative inverse, and this identity here is the multiplicative identity 1. So in another fashion, that's to say, when you multiply any natural number by 1, then we should get what? A again. So our multiplicative identity in this case is 1. So whatever natural number you have times 1 should get the same natural number. So 1 here serves as our multiplicative identity. Then let's look at the next property called division. Distributive property of multiplication over addition. Now, distributive property means that you are having, let's say, a multiplying b plus c. So when you have something like this, solving it, usually we go by the method where we will use a to multiply b and then a to multiply c. What we are doing is we are employing the distributive property of multiplication over addition. So it means we can distribute this multiplication over the addition happening in here in the brackets. So the same thing. So we are going to result into a times b plus a times c. This is simply what we call the distributive property of multiplication over addition. Now there are other properties outside of the addition, the division and multiplication. Let's talk about one here called the trichotomy law. Now the trichotomy law is talking about the relation between three different natural numbers taken at a time. So when we can have three natural numbers, say a, b and c, the trichotomy law is trying to tell us that one of these relations, so the first one is either that, sorry, let me clean this. So let's do it two natural numbers. So the trichotomy law is going to tell us that for these two natural numbers taken, it's either a equals b, or a is greater than b, or a is less than b. This is what happens when you take any two natural numbers at all. So provided a and b are members of the natural number set. So it's either that a is equal to b, or a is greater than b, or a is less than b, which is always the case. Now let's look at the law of transitivity. This is where we are going to consider the three natural numbers. The transitivity law. Now this is what the transitivity law is telling us, so belonging to the set of natural numbers. Now this is what it states: if a is less than b and b is less than c, then it should make sense that a should also be less than c. So let me represent it on a number line. So it's like saying a is here, so obviously a to the left of b means that a is less than b, and then we have b also less than c. Now on the number line we can see it clearly that a is also to the left of c, hence a is less than c. So that's what the transitivity law is telling us. We talked about the closure property, where any two natural numbers you add is also going to give you two natural numbers. So that's for the set of natural numbers. Now let's move to the set of integers. Now integers, as I said earlier, they are the positive and negative whole numbers together with 0. So a set containing all this is what we call integers. It's denoted by the letter z, the set of integers. So we have, say for example, -3, -2, -1, then 0, then 1, 2 to infinity. So this side also came from infinity then it continues to infinity. Okay, now let's look at some of these properties of the set of integers with addition and multiplication. So the first one we are going to talk about is the closure property of addition. Now, in addition, you can bear with me that anytime you take any two integers, so let's say, for example, -2 plus 4, this is going to give us 2. 2 is also an integer, the positive side of the whole numbers. So this gives us 2. So now this closure property is telling us that anytime we take two integers or two or more, 3, whichever you want to take, anytime you add integers, what you are going to get should definitely be an integer, and that's what closure property is. Now, commutative property of addition. It applies here to in integers as well as we did for natural numbers. When you add integers, so let's say a plus b, so a and b are integers, a plus b should be equal to what? B plus a. And that's what commutative property is. When you reverse the position where the numbers are, it should give you the same result. That's what commutative property of addition is talking about. And associative property, again, in the set of integers, when you have 3 integers and you want to add them, so you take 2 at a time, the result you get, you add to the other one. That's how basically addition is done. So a plus b, the result you get here, you can add it to c. It should be the same thing as adding a to the result when you do b plus c. And another way could be a plus c, then you add it to what? The result of this result, you add it to b. This is all associative property of addition. Now let's look at what we call the additive inverse property. So an additive inverse. So when we talk about additive identity. Now an identity is simply a number or one of such members of the set that when you operate it against any other member, you should get that member back. So let's say an identity is I. In addition, it means that a, which is an integer, plus I should give back as what? A. This I over here is what we call the identity. So let me illustrate it over here. Now when you do such, so a plus I should be equal to a, and identity property requires that your operation is commutative. So a plus I should be equal to I plus a, then all should be equal to a. Now let's take one side of the equation and solve. We'll get the same result. So it means that a plus I being equal to a, when we solve for I, we are going to get 0. So the identity element in addition on a set of integers is 0. So 0 is this unique integer we are talking about for addition on a set of integers. Let's look at the additive inverse now. The additive inverse. Additive inverse, it means that if, let's say, b, in this case, let's say a is our integer and b is the additive inverse, then when we operate a in addition with that additive inverse, then we should get the identity element of that operation in the set. So in the set of integers, we already found that the identity element is what? 0. So it means that if b is our identity, so a plus b should give us that 0. So it means b is our inverse here. So we should find for b. So a will be equal to, when we make a the subject, a will be equal to what? Minus b, or simply put, b equals minus a, because it's b that we are interested in. So it means this our inverse element is equal to negative a. So for any number in the set of integers a, its inverse is negative a under the set of addition. So under the operation addition. So when you are talking about addition on the set of integers, the inverse element of each member is the negative of the number. So a minus a gives us 0. So let me expand it. A plus negative a, because we are talking about addition. So it will be nicer when we put it in this form. So a plus negative a equals 0. Here the 0 represents what? Our identity element. Our negative a here represents what? Our inverse. And then a is basically the number we are taking from the set of integers. Okay, now let's move on with the next property called closure property of multiplication. And when we are talking about multiplication on the set of integers, it simply means that anytime you take 2 or more integers and multiply, your result should be an integer. So a times b should give us a result c, where a, b, and c all belong to the set of integers, so capital Z. So this is what the closure property of multiplication is on the set of integers. So it can be more. If it is 4 integers and you multiply, you should get a result which is also an integer. Now the commutative property, we looked at it in addition already. So commutative, when we reverse the position, so a times b should give you the same thing as b times a. So this is what commutative, we've looked at it several times. An associative property, as I've already described for the addition, is the same thing. So let's see, we've taken 3 integers, so a times b times c. Multiplication, as you do, you take 2 things, you multiply. If it is 4 numbers you are multiplying, you take 2, multiply the result, you use to multiply the next one, then the result you use to multiply the next one. That's how it is done on the basis level. So if you have 3 numbers, 3 integers a, b, and c that you are multiplying, then a can be multiplied by the result of b times c. So we have a multiplying b times c. It should be the same thing as multiplying the result of a times b by c. So what it means is that in this first case, we've multiplied b and c. Then whatever we got from here, we multiply it by a. It can also be done by multiplying a and b, then whatever you get from there, you multiply by c. Now, this is what we call the associative property. Now, let's look at the distributive property of multiplication over addition on the set of integers. As described in the set of natural numbers, is the same thing happening over here. So the distributive property, so a multiplying now b plus c is the same as distributing this multiplication over here over the elements in the bracket. So a times b, then you add it to a times c. Doing this is what we call the distributive property of multiplication over addition. The other laws also apply over here, like the trichotomy law and the law of transitivity. Now the trichotomy law, as we saw, when you have 2, so here we are talking about integers. When we have 2 integers a and b, either of these 3 cases hold. It's either a equals b, or a is greater than b, or a is less than b. Anything apart from this won't be valid, and it is always going to be the case. Now the law of transitivity, we saw that when we take 3 integers, so a, b, and c belonging to the set Z, we saw that when a is greater than b and b is greater than c, so this is the first condition. So in the transitivity, we say a greater than b and b is greater than c, then this should imply that what? A is greater than c. So this is what the law of transitivity is telling us. It can also be in different form. So we can also say a less than b and b less than c, then a is less than c. So this is from simple implication. closure property under multiplication also tells us that anytime we multiply two or more integers, we should result into integers. Now the last set we'll be talking about, if I'm right, no, the last but one, is a set of rational numbers. So as I've introduced, the set of rational numbers is a number. So a number that can be represented in the form a over b, where b is not equal to 0, is what we call a rational number. Now a over b is simply a fraction or a ratio. Now let's look at some properties of this set of rational numbers. Now the first one we can talk about is the closure property of addition on the set of rational numbers. Now when you have, so a, b belong to the set of integers. Now when you have a rational number, the first thing, so closure, so the closure property under, okay, let's talk about addition. So under addition, so what this simply means is that when you add two or more rational numbers, the result should be what? A rational number, and that's simply closure property. So for a b belonging to the set of rational numbers, a plus b should give us c, where c is also a rational number. Now rational numbers can be negative as well. So one common question is, so for example, -2 and 2. These two are also rational numbers because they can be represented in the form a over b, where b is not equal to 0 and a and b are integers. And -2 as a rational number is simply -2 over 1, and 1 is not 0, -2 and 1 are both integers. Now -2 over 1 plus 2 over 1 gives us 0, and 0 is also a rational number because 0 is what? 0 over 1. 0 is an integer, 1 is an integer, and the denominator in this case 1 is not 0, obviously. So this confirms everything we want to talk about the closure property. So anytime you add two or more rational numbers, then you should be expecting another rational number. Let's also talk about the commutative property of addition. So here we are talking about a set of rational numbers. So as we did before, is the same thing. So when you have two rational numbers a and b, which belong to the set of rational numbers, then you should expect that a plus b, however you do it in addition, should give you the same thing as b plus a. They are the same thing. Okay, now let's look at the associative property of addition on the set of rational numbers. Sorry. So let's denote rational numbers with Q, so that capital R for real numbers and Q goes to rational numbers. Alright, so the next thing is associative property. So when we have a, b belonging to the set of rational numbers, then for a third one, so let's say c, for the associative property, in addition, a plus b plus c, so we are adding a to the result of b plus c, it should give us the same thing as a plus b adding with c. So these two should be true for the set of rational numbers. So any three at all that you take from the set of rational numbers, this operation should be true. And here we have an additive identity property also on the set of rational numbers. Now when you are operating on the set of rational numbers, when we talk about identity, as I said earlier, it means that we are adding, so let's say a and plus let's call B our identity element. It means whenever we operate using an identity element, we should get back what? The number, so A. So we are calling B our identity element. And we did this already. So here we have to solve for B, which is our identity we are looking for. When we solve for B, we are going to get A minus A, which is 0. So it means 0 is the identity element under the set of rational numbers when you are doing addition. So that's to say A plus 0 is A. So quick examples like 1 plus 0 is 1. Anything you add to 0 is going to give you the same thing. And so 0 here is our additive identity property. And additive inverse also says that whenever you do, for example, A plus B, we should get the identity. So this is what identity does for us. So it means that here B being our inverse element. So this B here is our inverse element. And I here is our identity element. So A is a random number from the set of rational numbers. And we are adding it to B. B here we are calling it our inverse element. It means that we should get our identity element. And we've already found that our identity element under addition is what? 0. So it means A plus this inverse element should give us 0. Hence, B is equal to negative A. Okay. So the other properties are the same, like the associative property of multiplication where we saw is the same thing. The commutative property is also the same thing. And the law of transitivity also the same thing, where we have A less than B and B less than C, then A is less than C. It's the same thing also that works over here for the set of rational numbers. Now, as I said, irrational numbers is simply anything that's not rational. So you cannot represent an irrational number with A over B where B is not equal to 0. It's not possible to represent it. Where I made a quick example that pi is irrational, and hence 22 over 7 is an approximation of pi. Pi itself is irrational and non-terminating and non-recurring. So that's the set of irrational numbers. And next time we meet, we'll talk about the well-ordering axioms and the principle of mathematical induction. Thank you.